Hey everyone, a very happy Tuesday and welcome back to our ARM Tech Talk series. And if you celebrate it, happy Halloween. Sadly, I'm not adorned in any Halloween themed costumes, but very much happy Halloween. If you are celebrating that today, it's great you could join us for our ARM Tech Talk series. If you haven't been to one of these before, a particular welcome to you. This is the place for the latest and greatest trends, technologies, and best practices from ARM and our ecosystem partners. I'm super excited today that we're joined by Linaro, who are going to be talking about protecting compiler optimizations for ARM with Linaro Benchmarking CI. We've got a really great in-depth technical tech talk today for you to kind of enjoy and really enjoy the technical detail of it. And before I hand over to Maxim, I've got a couple of little housekeeping items I'd love to just go through. So Maxim, if you wouldn't mind heading to the next slide, that'd be great. So you can tweet us. Please use these hashtags when doing so. We'd love to hear where you're joining us from. You can also use these hashtags, of course, on LinkedIn. We'd love to hear what's inspired you today from today's tech talk. I think this might be our 80th tech talk. So all 80 tech talks are available on demand, including this one. This one will go live immediately on YouTube after today's talk. And all of our upcoming talks are available on arm.com/tech talks. And talking of upcoming tech talks, I'd love to give you a little sneak peek of what's coming up, which is on the next slide. We've got on November 7th, if we can flick to that, that'd be great. Thank you. November 7th, we're talking about smart cities with Renee Sesok-Turis and ourselves from ARM. So really excited for that one. And then we shift gears, part of the automotive play here, play on words, over to Sensory, who are going to talk about their work with Sophie and voice AI solutions for the automotive market. So there's a lot of great content here, and we've got even more planned out for the rest of the year. Some really exciting enhancements to the platform as well coming, as well as some really great topics. So I'm super excited for those. But most importantly, you're here today to hear from Linaro. So if we head to the next slide, Maxim, it's my great pleasure to introduce Maxim from Linaro, who's going to be giving today's presentation. If you want to flick your camera and microphone on, Maxim, whenever you're ready, that'll be awesome. Here he is. He'll be giving today's presentation. So that's enough for me. But before I hand over to Maxim, one final reminder, if you've got any questions during today's presentation, you know the drill if you've been to one of these before, please use the Q&A box in the Zoom menu bar at the bottom, and we'll get to those at the end. I'm sure you're going to have a ton of questions, Maxim. It's a really great in-depth technical talk today. So Maxim, thank you so much for joining us for today's ARM Tech Talk. Please take it away.
Thank you, Tobias, and hi, everyone. I'm Maxim, and I lead toolchain development at Linaro, and I have been doing toolchains all of my professional career, and my focus and love is with compiler performance optimizations. So in today's talk, we are going to discuss how Linaro is using automated benchmarking to protect compiler optimizations in GCC and LLVM and the related toolchain projects with automated benchmarking, automated result analysis, and how we follow up with upstream developers when we detect problems. Let's start with a quick coverage on how much benchmarking configurations we are tracking. So we are tracking two toolchains. In GNU toolchain, we track all the parts which are related to performance, binutils, GCC, and glibc. And on LLVM side, we are tracking LLVM monorepo, which has both C, C++, Fortran, and other compilers. We are doing this for a variety of compilation flags. Code size, optimize for code size, optimize for usual code speed, -02, and for more aggressive O3, with and without LTO. And we are tracking code speed, code size, and code vectorization metrics. In the presentation today, I will focus on code speed and code size, because code vectorization metric is still somewhat in development. And if there are questions about it, I'll answer those, but otherwise we will focus on code speed and code size. For benchmarks, we use spec CPU. On one hand, it's a very well-established CPU benchmark. On the other hand, it's also quite difficult to run and get reliable performance results for, so that you can use those results in automated testing. So our thought was that if we will be able to make spec CPU 2017 speed behave in our system, which uses OpenMP, which can run on several CPUs in parallel, then we will be able to handle pretty much any other benchmark. We handle two targets, ARC64 Linux and ARM-HF Linux. And you can see a list of our benchmarking pool. We have hardware from the teeny tiny ARMv7 boards up to the HPC server class hardware. So what is the problem statement that motivated this project? At Linaro, we are one of our responsibilities is to keep upstream projects in good state for ARM architectures. So we wanted to monitor tip of trunk repositories of upstream toolchains, LLVM, GCC, glibc, binutils, and also newlib for bare metal testing. And once something bad happens, in the sense that performance decreases or code size increases, we wanted to know which patch caused that. And we wanted to do that in an automated way. So we wanted to build a system that tracks tip of trunk branches of the upstream Git repositories and notify us when one of the benchmarks increases by a couple of percent, either in code speed, in code size, increase in code size, or performance drops by a couple of percent. We wanted to know about it. Or if one of the hot functions, for example, symbol runtime, increased by more than 10 or 20%. And we wanted to do this across a wide variety of different configurations. So, for example, we wanted to track code speed at -OS, -OZ, with and without LTO, and we wanted to track code speed at -O2 and -O3, with and without LTO. Do this across two toolchains, two architectures, and potentially across a range of different microarchitectures. Why we think that this is an interesting and important problem to even consider? On one hand, benchmarking is difficult, and it usually takes between days and sometimes 1 or 2 weeks for a good benchmarking experiment to set up and run manually. And because this is a non-trivial amount of effort, the usual practice in the compiler teams is to benchmark compilers at release points. So to compare, for example, LLVM 17 against LLVM 16 and make sure that LLVM 17 performs better or the same, but definitely not worse than the previous version. Similarly for GCC, compiler teams often benchmark next version of GCC against the previous one. But let's say you see a degradation in performance when you benchmark a new compiler release. At this point, there is not much that you can do because it's often the project policy that only correctness changes, only correctness issues will be addressed in the release branches. And also, it may be that the change which is causing bad performance now was committed 3 months ago. And the developer has moved on and is working on the next project and may have lost interest in the previous project, or his or her manager just does not allow allocation to support time allocation of the engineer to support the previous project. So we wanted to make a system that will detect regressions in the mainline branches of compilers within days or maybe a week of them hitting the mainline. If you do that within a week of the patch being merged, developer is still psychologically invested in that change. And if you just shoot him or her a note that, hey, your patch have caused 5% degradation on this benchmark, there is a chance that they will get curious why that happened and will allocate some of their time to investigate this problem and hopefully fix it. So now let's see some of the case studies for what the system has produced and what is our plan on handling these reports. These are static slides, so this is a screenshot, but if you click on it in the PDF version, or if you use the QR code in the live version, you will actually go to the report, which is in Linaro's public Jira, and you can see what's happening here. So this is the output of the system. It automatically created a Jira card, which managers love, that a specific commit of LLVM caused 42% increase in this C++ function. Because it's generated automatically, we just put the biggest regression with the biggest number as the title, but if you scroll down, the details are much more interesting. So this is a commit from an Intel engineer. It happened about a month ago in September, and something to do with handling error in math code. And we see that this change, this single commit, has caused LLVM to grow by 2%. At O2 configuration, so this is not really interesting because O2, LTO code size can grow, so this is not a big problem. This is starting to get interesting, that we have a single function growing by almost a half from a single change. So this may be an interesting case to investigate for the patch author. Continue to scroll down. Again, this is -OS optimization level with LTO enabled. The whole benchmark grew in size by 2%. So if this 42% is for a single function, this is for the whole binary. And this is not an isolated case for this binary. It also happens at OZ. Code size increases. And there are quite a few reports about LLVM here, all for code size. But if we scroll down, we get into the code speed, so this is code size for Spec 2006. which has an earlier version of the same benchmark, so roughly the same reports. So we know that this benchmark code size affected by a dispatch. But now we get into the code speed section. And if 2% code size on a single benchmark is okay, can be tolerated, it would be ideal if it didn't happen. But 16% on code execution benchmark, on another code execution benchmark, is concerning. And this is a Dasho2, which if we have reverted dispatch, this benchmark would now speed up by 16% compared to the status quo. And again, we can confirm that this is not a very isolated incidence, because if we also see 31% in a particular function, slowdown at spec CPU 2017 speed. So any individual report here, any of these reports individually would not be a very serious problem, but all of them combined show that this commit would worth investigating. And we can even see some details on why that slowdown has happened. So in this configuration, the 22% slowdown came from the 34% slowdown in a single function. So hopefully it should be relatively easy to investigate the cause of that. And this commit was merged on September 19th. And we got the very first report on the same day for code size. And then we got the very first report about the code speed on the next day of the commit hitting the mainline. And then over the next week, over the next 6 days, all the other reports came in and were integrated into this Jira card. This is not an isolated case. So let's look at the next card. This was from Intel. So this patch came from Intel. This one came from AMD. It's a code gen change, which changes how register allocation works. Actually, it was merged on the same day. That's a coincidence, but it was developed slightly earlier, but was got into LLVM mainline the same day. So let's see what it has. Just a single, very minor code size improvement in a single function at -z, not too interesting. But in the code speed section, we see that spec qsort MCF function slowed down significantly. It appears it did not cause a significant overall regression. So maybe it's just performance, or rather cycles went from one function into another function, so not a big deal. But this 6% slowdown and this 7% slowdown is something interesting, and that could be investigated. So let's see. For 6% GCC slowdown was caused by 32% slowdown. And for a single function, that's a lot. in a single bitmap IOR_into function. And if we see, if we just look at the numbers here, so performance samples are a measure of time. We see that here we have about 1,800 additional perf samples due to this change, and the same, and the overall benchmark cycles increased by roughly the same amount. From this point, we can open up execution profiles of this function and see and check what the patch do to cause this regression in the behavior. Again, if we look at the history of how long it took this problem to be detected, it took 2 days for the original report for the very first regression to be detected, and over the next 4 days, we detected regressions in several other configurations. I'll have just a couple of more of these, and then we are going to jump into a slightly different discussion. So not only Intel and AMD are responsible for regressions on ARM, sometimes optimizations intended for code speed, for example, can cause code size problems, right? So this patch, which seems to be a good optimization, has an interesting corner case, which occurs only in a very particular set of circumstances. So it's 6%, which is significant in BZIP code size increase, only at ARC64, only at dash OS with link time optimizations enabled. Other regressions are not very significant because they don't change the overall binary size measurably. And some slowdowns in these benchmarks, but 4% potentially can be tolerated in the video encoder benchmarks because they are quite sensitive. So they go plus minus 4% very often. The point I want to address here is that not all of these commits are necessarily regressions, but all of these commits are interesting in the sense that they show parts of LLVM or GCC compilers, changes to which can cause significant changes in benchmarks. So, for example, if all you care is BZIP because your file server all does compression all day long, and it's really important that your home video server or media server compresses your home videos quickly, then, or you sell such an appliance as a media server, then you really want some of these applications to be compiled as quickly as possible. And you don't want to see regressions when you switch from an older version of the compiler to the newer version. And this is our next investigation. So it's another register allocation commit in LLVM. And I think the interesting parts here are, again, 9% code size regression in BZIP, but only for ARM. Google can be expected, or Intel or AMD or anyone else, to test every single of their changes on a 32-bit ARM machine and make sure that their changes, which may very well improve code generation for 64-bit architectures, do not regress code size or code speed for 32-bit architectures. So in this sense, Linaro positions itself as a gate, not as a gatekeeper, but as a watcher to catch problems quickly when they occur. Because it's an open source community, people try their best to make all of their optimizations as good as possible. But we cannot test every single benchmark on every single architecture before committing it as part of the development process, before merging into the main repository. So, but at the same time, interested companies like ARM, like Linaro, and like Linaro members do want to monitor upstream compilers and make sure that the code they produced a year ago for the important applications is the same or better now a year later. Final example I want to discuss is all of the regressions that we looked at before were across many configurations. The same commit both changed code size and code speed on various benchmarks. And that is important. Sorry. And this is important if you care about all of the ARM ecosystem. But what if you care just about a very specific open source project like Perl Bench, and that your software product or your appliance, hardware appliance that you sell, runs just a single application, but it runs at 100% of the time. You don't really care what happens to the rest of the benchmarks. You care about your primary application. And this system allows you to monitor a single application and detect corner cases where its performance regresses. Like in this case, this commit doesn't cause any problems on 90% of the software. But if all you care is Perl, then it really affects you. And this is another similar case when commit doesn't change code size, doesn't change performance on none of the 20-something Spec 2017 benchmarks and on none Spec CPU 2006 benchmarks, but one, Blender, at the default compilation flags. But if all you care is Blender, this is important for you, and you want to investigate if this problem can be avoided by investing few more hours into improving this change. Okay, so all these examples, I have specifically look at the start date. I have specifically chosen these examples, not across the last year or even the last 6 months of LLVM development. All these examples are detected within the last 2 months, September and October. So these are not rare cases. We now have a long history, and it keeps growing, of the problems detected. And on average, each week, we detect 1 or 2 of the regressions for LLVM, and about 1, so slightly less, for GCC. Maybe it is simply an accident that GCC has been a bit more stable lately than LLVM, because LLVM just started a new development cycle recently. But yeah, we are catching quite a few of these problems. And this is the last slide from the presentation, which just shows the guiding principles that we are using in Linaro toolchain CI. Engineer time is precious, and that's the most important one. We want to automate everything that is reasonable in the difficult engineering tasks, and benchmarking and initial performance analysis is time-consuming, but it can be automated. At the same time, machine time is not precious, but is limited. We don't have all the compute power in the world, so we need to be smart at how we build the system and benchmark the project. And the final one is the understanding that upstream projects move faster than we can build and test. LLVM project gets about 4,000 commits per month. That's about 1,000 per week, or 100, from 100 to 200 a day. We cannot benchmark every single commit. So we have to use smart bisection techniques to be able to find single commit regressions. And because engineers' time is precious, and that's not only in our team, in the downstream team. This also applies to the upstream developers and upstream communities and their time. Upstream developer can be encouraged about spending time investigating a problem that I have, only if I have very good arguments that it was his specific or her specific patch that caused the regression. So we need to have single commit reports. Also, when we make these reports, we need to provide developer before and after comparisons for optimal investigations. And this before and after should be 1 commit apart. And relative results are most interesting. Absolute results are less useful unless you are looking at the history over time. But yeah, these principles and these consequences of these principles really helped us design the system. So this is the end of the presentation. What are your questions and comments?
Thank you, Maxim. That was awesome. Awesome presentation. And do you want to just quickly mention in terms of for follow-up, I know you put your email address there, so would love to just talk about that maybe briefly just while we get some questions coming. I've got a couple.
Okay. If you have any questions later, if you think about something interesting you want to ask later, feel free to reach me on my email address. Or if you have a question about something secret you don't want to discuss publicly, also reach me out at this email address.
Thank you. That is great. I'm sure there'll be lots of people reaching out with secret things as well. So let's jump into the questions. I've got a couple, but audience, this is your time for questions. So do use the Zoom Q&A box. We've got some time for questions, so I'll definitely make sure we get to them. So you've showed off the benchmarking system, and it's got a lot of moving parts, right? So how do you handle random or let's say transient as well infrastructure errors in this?
So indeed, let me look for the. This is really a question of how we handle benchmarking board just crashing, or a Git server not being accessible when the job starts.
Yeah,
we handle this in a transactional approach. So all our results from the benchmarking are committed into a Git repository, which we use more like database. And the action of pushing results to become the new baseline is done at the very end of the job. So if the job fails for whatever reason, that means that the results of the job are just not committed, and the next CI loop, when it runs, when the next build runs, will start from the same state as the previous failed job. And this is, so this slide shows the Git repository of the results for one of our configurations. And here, yeah, you can see that, for example, build 107 doesn't have results here because something may have happened to it. Maybe it was a legitimate failure, maybe it was a sporadic failure, but some of the build numbers are missing here, specifically because they have failed.
Gotcha. Thank you, Maxim.
Okay.
That's great. And what about when it comes to the let's say compiler revisions, right? Do you test every revision of compilers on one of the ARM boards?
We would not be able to do that even if we tried. So this goes back to the question, or rather to the consequence that, so to one of the principles that upstream projects move faster, that we can build and test. In LLVM, we get commit pretty much every hour, if not more. And to run spec 2017, even if you parallelize it across many boards, it will still take you an hour. So we are doing bisections to have a complexity of our testing, a logarithmic complexity, rather than a linear complexity of our testing, compared to the number of revisions that we have to test. So that gives us ability to trigger every project. So let me see. I think I may have a good. Yeah, so here you can see that results are pushed about about once every 3 or every 4 days. And this matches the frequency of how often this configuration is triggered. And if we detect that in the last 3 days, we have had the commit that caused a performance slowdown or code size increase, then we bisect the revisions for the last 3 days. And that will take us 10 hours to bisect. But the trick there is that we can bisect only on the benchmarks which have regressed. We don't have to run the full spec test suite benchmark, the full spec test suite. We can, if we see that only bzip has regressed, we can run only that one benchmark, and it's much, much faster.
Gotcha. Thank you for that. And we've had a question come in around the techniques that you use. What are the techniques you use for reducing the noise in the benchmarks? Do you take into consideration hardware noise as well as software noise?
Yes, for both. So for the, let me go to the slide about our benchmarking hardware. First of all, we use the best practices for benchmarking. And that means that we fix frequency. So for the hardware side, we fix frequency, we stop all the non-necessary, non-essential services, we reboot the board before the benchmarking. And actually, I may have some slide. Yeah, so we reboot the board, we fix CPU frequency so that its scaling governors are not changing the performance of the board, and then we bind the benchmark to a single core if the benchmark is not using OpenMP, or we bind it to a single NUMA node if the benchmark requires OpenMP and several cores. Let me look at the software side. But even with that, we will have some noise. And the trick with that is when we look at the benchmarking data, we are looking at the interesting symbols primarily. These are the most hot functions, which account for roughly 90% of the execution profile. And I will switch between 2 slides here. So here we have a history of results, which has tens and hundreds of entries, which are all individual benchmarking runs. And some of them are runs for exactly the same compiler version. Some of them are runs for different compiler revisions, but the compiler, for example, did not, changes in the compiler do not result in changes in all of the benchmark functions. So in this case, we have a highlighted bways function, mat times vec. And this function before and after the change has the same MD5 sum, meaning that its assembly stream is exactly the same. And at the same time, this benchmark has just slightly different performance, just under 0.5% difference between these 2 runs. And we know that from this, we are able to say that this function has a variability of about 0.5%. And we can extend this because we have a lot of data points, we can calculate expected variability for every function and for every benchmark. And this allows us to have custom thresholds for every function and for every benchmark, exceeding which we consider performance drop to be a regression. But if performance drop is within that threshold, which is custom for every function, then we don't consider it to be a regression. So it's statistical approach to detecting when regression is within noise levels or when it is outside of the noise levels.
Gotcha.
It's slightly difficult to tell in words, but yeah, if you think about this, that if you have the same function with the same assembly stream showing different performance between runs, then you can make judgment of what is roughly the noise level of that particular function.
Makes sense. Makes sense. Thank you, Maxim. That's really, really great. And we've probably got time for just one more question from the audience. I've got one very quick question is, what happens when that, you know, you mentioned about the kind of patch authors earlier. What happens if they're not interested in fixing a problem? What do you do?
That happens. So let's go to one of the examples here. So one of the big reasons can be that even if the patch author is interested, but doesn't have ARM hardware to reproduce a performance problem, what do you do? Our approach is that we try to catch the problem within the short time frame so that patch author is still interested in that patch they have just merged. But if they are not interested and the problem is big enough, like for example, one of the first examples here, which shows a regression across many configurations and both code size and code speed. Well, if we don't get engagement from the patch author, then for big regressions, we'll have very good compiler engineers in the team who will analyze this problem and will either open up a bug in the upstream Bugzilla, or we will just fix it ourselves.
Gotcha. That's great. Thank you, Maxim. That's really, really great. And I think that about wraps it up. We've got no further questions have come in. So is there anything final you'd like to say to the audience before we wrap up today's Tech Talk on your side, Maxim?
Benchmarking is a very interesting and very tricky activity. And I think that it is important to benchmark not only the most widely used configurations, but also track code speed of -OZ configurations, for example, and track code size of -O3 configurations, because when you do that, you can get very interesting reports, even from and catch problems that a reasonable person would not be able to anticipate, like an NFC change, a supposed NFC non-functional change, changing code size. For example, that allows you to have good starters for conversations with upstream developers. And one final note, Linaro, all Linaro is doing is open source. So including our Jira and our plans, everything is open source and public. Well, everything we do is open source, and our Jira is public. So go ahead and look at our Jira in search of regressions for your favorite benchmark.
Thank you. That's a super comprehensive wrap up. I mean, what a great tech talk, really technical details on a whole bunch of great topics. And Maxim, thank you so much for a great presentation. Audience, thank you so much for attending today's ARM Tech Talk. Tune in at the same time next week, although because of the time zone changes, if you're in the US or elsewhere in the West Coast or East Coast of the US, it's an hour earlier, so 8 a.m. Pacific, not 9 a.m. Pacific. That's 4 p.m. UK time next Tuesday for another ARM Tech Talk, where we're going to be talking about the smart city. So that's a really exciting tech talk to attend. Do tune in same time next week for that. So Maxim, thanks again so much for a great tech talk. Audience, thank you so much for attending. And we'll see you again same time next week for another tech talk featuring the latest trends, technologies, and best practices from ARM and our ecosystem partners. Thanks so much, everyone. Bye-bye.